Black holes. They're beautiful, aren't they? But what exactly are these spectacles of space? And these holes are some of the most misunderstood phenomena in our whole universe. And on this journey, I will tackle some of the questions that arise from their presence alone. What proves a black hole exists? What are Einstein's theories of relativity, and how do they connect us further to black holes? Why is image embedding and gravitational lensing a key step to proving the existence of black holes? Yet, what drove me to these questions all started with my pursuit to answer this. Is the evidence that supports the existence of black holes enough evidence to support the existence of wormholes? Strap in and let's explore the cosmos. It all starts over 100 years ago, September 26, 1905. Einstein's theory of special relativity. One of the most memorable theorems in all of science. The theory proposed a radical idea. Space and time weren't absolute, but relative to one another. We now know this concept as space-time. A complex topic to fully wrap your head around. But let me provide you a thought experiment to help better your understanding. Space-time is most easily thought of as space and time by themselves, just like what you're experiencing right now. The only difference is someone else could be experiencing a different measure of time or a different measure of space. And when the time changes, it's called time dilation. Take for example, if I was on the outside of a train, inside. Whoa, that was crazy. But what I was saying was, if I was on the inside of a train and I was looking at a mirror that was 5 meters away, and now if I take out my flashlight and I shine it at the mirror, it bounces back. Normal, right? Something odd happens when you're viewing this phenomenon from the outside. The train never stopped moving, so the light traveled towards the mirror, and the mirror moves sideways to my relative spot on the platform. This causes the light to appear as if it's traveling diagonally, making the light seem to travel more than it actually did. This is the fundamental theory of special relativity. Simple sounding now, but then it was a revolution. Whoa! Einstein had two supporting postulates with his theory. First, the consistency of the speed of light, which states the speed of light, c, is a universal constant and the same in any inertial frame. This is basically saying the speed of light in a vacuum is the same for all inertial viewers, regardless of the observer's motion or the source's motion. Nifty, right? Right? Einstein's second postulate, the principle of special relativity. It states the laws of physics are the same in any inertial frame, regardless of the position or velocity. This postulate is basically saying your position or your velocity of the observer or the source is relative to the observer or the source. No matter who, the two must follow the laws of physics. Like this guy. Looks like a real rule follower, doesn't he? Okay, now that we have a grasp of space-time and the theory of relativity, it's finally time to talk about black holes! A black hole is an incredibly dense piece of mass that creates a hole in space-time. And this hole is a concentration of a lot of mass into a tiny bit of space-time. Fun, right? A stellar mass black hole can compress a star with 3 solar masses, which is 3 of these bad boys, into a sphere with a radius of only 9 kilometers, which in freedom units, that's 5.6 miles. And if you're wondering how big that is, it's about as big as this picture I found on Google. Wow. We may not know what's past the event horizon, the surface of the black hole, but there is a lot we do know, especially like how Einstein's theory of relativity connects us to black holes. A key piece of evidence of Einstein's theory is how it describes gravity not as a force like how Newton says, but as the curvature of space-time caused by mass and energy. Yet, science grew even more profound. 1935, Albert Einstein and Nathan Rosen proposed a radical idea. This idea was a theoretical shortcut between space-time, known as wormholes. Wormholes connect 2 separate points of space-time via an Eisen-Rosen bridge. Though only theoretical, scientists hypothesize that it will be able to travel drastically faster than the speed of light. Additionally, a wormhole would likely need an abundance of negative energy to stay open, which we currently don't have any way to get this much negative energy. Like, it's a lot, like too much. Although wormholes aren't very well known, and strictly theoretically currently, I postulate that the existence of black holes is enough evidence to support the existence of wormholes. Now, let me prove to you that black holes exist, and why their existence can prove the existence of wormholes. I want to start with one of the most irrefutable pieces of evidence that we have, the image of a black hole. The accumulation of all our research we have done on them, but in order to understand how we capture this image, we must understand what captured the image. Let me explain. The imaging of a black hole starts at the Event Horizon Telescope, or the EHT for short. The EHT is a conglomerate of multiple other telescopes to functionally form as a giant telescope, each with extreme magnification and different medians, such as X-ray and radio waves. Black holes are very, very dense, which means the surrounding material gets pulled in at rapid speeds, causing the material to heat up and emit X-rays. The EHT then captures these X-rays as a magnified image. This is M87, the first imaged black hole in the history of mankind. Located nearly 53 million light years away, or 318 quintillion freedom miles away from Earth. That's farther than when your grandpa had to walk to school. NASA's next step was to capture the image of the supermassive black hole at the center of our galaxy, Sagittarius A. Using the Event Horizon Telescope with some additional new telescope to the gargantuan telescope known as the EHT, they were able to create a new magnified image, at least simply said. For context, Sagittarius A only covers about 1/13 of a billionth of the night sky. Yeah, that's small. Which goes to show how impressive this accomplishment really is. Subsequently, I have another technique used to fully wrap our heads around a black hole. This technique is known as image embedding. When we think of the structure of a black hole, this is usually what we see, where a singularity bends space-time down to a single point. Since a black hole is so dense and its gravity is so strong, it creates seemingly a hole to the outside observer. This image embedding allows us to fully grasp that idea. More importantly, it's also how we visualize wormholes. See? The Einstein-Rosen bridge is there. It connects the two separate points of space-time. Using the same idea of both structures in image embedment, both relate to the ludicrous idea of manipulating space-time. Last, but not least, gravitational lensing. Cool, right? Gravitational lensing by a black hole occurs when its immense gravity warps the space-time around it, bending light from the background behind objects, making them appear distorted, magnified, or as multiple images to the distant observer like us, effectively turning the black hole into a powerful cosmic lens that allows astronomers to study its presence, mass, and effects on the universe, which I think is pretty cool. The black hole distorts the space around it, which warps the images of stars lined up directly almost behind it. This phenomenon, along with the other following phenomenons, proves that black holes most definitely exist. But why does knowing this help prove wormholes exist? Well, in reality, we can't say with any certainty that they do exist. But we can consider the past. Initially, the existence of black holes was only theoretical, a mystery to us. Only Einstein's theory backing it. That was until the past 2 decades, where he found solid evidence of their existence. And I believe that wormholes are the same, only backed by Einstein's theory until proven otherwise. That's why you should believe with me. Believe wormholes exist, and that the existence of black holes support it. Thanks for exploring the cosmos with me. Now until next time. Wait, that's a black hole.